This is a short presentation on the effect of inductors in a circuit. What we will consider is a very simple RL circuit. R and L are in series with a battery, and we have a steady current I sub 0, which is simply V0 divided by R, flowing from the battery through both the resistor and the inductor, as shown in figure 1. This is the steady state current. Then at t equal to 0, we flip the switch to disconnect the battery. The resulting circuit is shown in figure 2 without the battery. Clearly, just before t equal to 0, we have the full current I sub 0 flowing through the inductor L, as shown in the direction shown. The same current will also be present just immediately after t equal to 0. What we are asking is, how does the current for subsequent times t greater than 0 behave? So this is what we're going to try and learn. Just after t equal to 0, the current has to decay since there's no battery. The decaying current generates an EMF, or a voltage, across the inductor, which of course is given by Faraday's law. E equals minus L delta I divided by delta T. So the EMF clearly is proportional to L. Larger the inductor, larger the EMF. And of course, it's also proportional to delta I delta T. That's the rate of change of the current. But the question is, how do we know what the rate of change of the current is? To answer that, we're going to go through this little exercise. Now, the voltage that is across the inductor, you should recognize, is the same as the voltage across the resistor. Why? If this is not clear, let's take a look at another way of writing the same circuit. You can rewrite the circuit shown here on the top as follows. So the resistor has been moved to the bottom arm, and you can see that the inductor and the resistor can now be thought of as being parallel to each other. So these are the two points, and with respect to these 2 points, the inductor is on this side and the resistor is on the other side, and you can think of it as being in parallel. So therefore, the EMF, or the voltage across the inductor, has to be the same as the voltage across the resistor. So this gives us the relation that the voltage across the inductor minus L delta I delta T equals I times R. This relation is valid for all times, not just at t equal to 0. We can rearrange this equation and write delta I over I equals minus delta T times R by L. So we've just rearranged terms so that I goes to the left side and the inductance comes to the right side, and so on. We're going to call this as equation 1. So we start from equation 1, so that equation is reproduced here. Now let's ask, what does this equation tell us? It tells us quite a bit. It states that the fractional change in the current, which is on the left-hand side, is a constant no matter what t is. In other words, we can place the time interval delta t wherever we want along the time axis, and the fractional change delta I over delta t at that time is the same. Now, what does this mean? Let's try to look at it graphically. So what we have here is the current as a function of time, and at t equal to 0, we know clearly that the current is I0, which is V0 by R. Now, we're going to wait a certain amount of time delta t. It doesn't matter what that time is. We're going to wait a certain time such that we drop the current to 0.9 I0. So the change in the current we are creating is 10%. Now, what this equation says is that if I move to a later time, this fractional change delta I over t at that time also has to be 10%. So in other words, for example, if I take a time over here where we have written 0.37 I0, where does that come from? We'll come to that in a second. So let's say the current is decaying, so over here it has to be something smaller than what we had before. So let's say it's 0.37, and 10% of 0.37 is 0.037. So the decrease in the current at this time, 0.037, is certainly much less than 0.1 that we had before. And it's proportional to the value of the current that we had here, which is so much more or less than the current that we had there. So that's the point of this equation. So whenever you have this sort of a dependence where the change in the value at any given time depends on the value itself at that time, you get a function that's exponential in nature. Exponential behaviors are very common in physics as well as in other parts of science. Exponential is a very common phenomena in the rise of the population with time, for example. And it works the same way. The number of people who grow or who are born in any given generation is proportional to the number of people who are in the previous generation, so and so on. So the equation for an exponential is written this way. So the current I at t equal to 0 we know is V0 by R. So when we put t equal to 0 here, we should get the original current. And at a very long time, t equal to infinity, we know the current dies away. So that indeed is given by this equation. The factor tau is a time constant which characterizes how fast this exponential curve drops down, and that's simply L divided by R. So L divided by R has the units of time in seconds. Now where does this 0.37 I0 come from? So 0.37 I0 is simply the number that you get if you take this time equal to tau. So e to the power minus 1 will give you 0.37 I0.